All right, welcome to Physics 2211, Lab 1. This is constant motion. All right, so let's get into it. So what is this experiment? So we're comparing constant motion simulation that I made on GlowScript with the starter code to real-life motion of a marker across a table. So constant motion means no net force acting on the object, or in other words, F net equals 0, as you can see here. And real-world motion is not constant because of extra forces which may occur, but we're going to be testing what the extent of those extra forces are, and Newton's second law will still apply closely if the net force is close to 0. So Newton's second law states that an object in constant motion will remain at a constant velocity unless there's a net force that acts on it, and we are proposing that since the velocity is constant, then there will be no net force acting on the object. All right, so basic rundown of the results. The velocity seems to be relatively constant. As per the graph, the orange dots are the simulated velocity from the GlowScript code, and then the blue dots are the actual data from the marker rolling across the table. So the results and the graph will be explained more later in the presentation, but right now it's important to know that the data is relatively close to the expected values. All right, so the simulation code, some important parts of it is that the original position of the ball is at 0, 0, 0, or at the origin, and then the velocity of the ball is going to be this value, which was just pulled from the data that we'll analyze a little later from the actual marker rolling across the table. You can see here on the velocity graph, it's constant at the 7.553 roughly. And then F net equals the vector 0, 0, 0, which means that just the net force equals 0 because it is moving at constant velocity. And then for the update formulas, the velocity remains the same since this term will be 0 because F net equals 0. So the ball mass and the delta t don't really matter all too much. And the ball's position will be updated due to it having a velocity, which we then multiply by our small time step delta t, in order to get the new position at each time step. So now the real world scenario has some error sources. There's not exactly 0 net force. It's pretty close, as we saw on the graph earlier, but the marker may slightly slip on the table while it rolls. The video scale may not be exactly accurate since we were using the wide angle lens when we were recording, and we were pretty close to the marker, so it might be a little distorted on the video. It's also difficult to accurately pick where the marker is at a specific time on the video. I was trying my best to keep it at the same spot on the marker every time, but there's just human error in that. And the marker is also not a perfect cylinder. The table may not be perfectly smooth. There may be bumps, there may be divots that might cause the marker to move slightly erratically. So the net force is not going to be exactly 0, but it will be pretty close. And now the setup of the experiment, as you can see here, we had the marker rolling across the table next to the ruler, which we use to calibrate the video. And then this video was inputted into Tracker in order to measure the position every frame. Then the data from Tracker was then put into Excel with the data received by the code from GlowScript, and then we measured how close it is to the ideal scenario with the same average velocity as explained earlier. So now here's a more detailed version of the graph I showed earlier. Here's a best fit line, which is very, very close to the orange simulated data. And then here's how close it was to the simulated data. This is the R squared value, which is 0.9994, which is very close to 1, and 1 would be ideal. So the trend line is shown. The simulation data follows a very linear path, as it is constant velocity in the simulation. But the real world data is very close. The marker was moving at very close to a constant velocity throughout the entire path. And the net force was very close to 0 in this case, since it was very close to the simulated path. Now, what does this mean in terms of the physics concepts? Newton's second law applied very accurately to the object as it remained in constant motion since there was no net force acting on it. However, there was some sub-perfect adherence to the data due to what was mentioned earlier, such as weirdness in the marker's shape and all of those things. But overall, the experiment was very successful in showing the movement of the object in constant motion and the balanced forces acting on it in order to yield a net zero force. All right. Well, thank you for listening, and have a good day.